We are now in chapter 3, energy bands and charge carriers in semiconductors. Now this chapter covers bonding forces and energy bands in solids, charge carriers in semiconductors, carrier concentrations, and drift of carriers in electric and magnetic fields. It also covers the invariance of the Fermi level at equilibrium. So we are going to look at all of these concepts. Now in chapter 2, we looked at the case of an electron in an isolated atom, where we said that the nucleus consists of protons, which are positively charged, and neutrons, which are neutral. And around the nucleus, we have electrons orbiting in a wave manner, like that, around the nucleus. Now, if you recall the energy bands of hydrogen, when we looked at the simplified case of the Schrodinger's equation for a one electron case, we said that the electrons can only exist at allowed energy levels, and these energy levels were given by something like minus 18.4 divided by n squared, where n is the energy level. Now in the case of a solid, instead of having these discrete energy levels where electrons can be found, we have now bands. So you get a band, and what a band simply means is that you have these energy levels, but they're now very close together. They are tightly pegged such that they seem to be continuous. They'll be like a band. They're so close to each other, and they seem to be like one thick energy level, so to speak. So in this chapter, we are going to try and understand how we come from here and get to that. Okay. But before we look at the energy bands, let's just try and see what holds a solid together. And we are going to do this step by step by starting to look at metals, then we go to ionic solids, and then we look finally at covalent solids. So in ionic solids, we have an example of sodium chloride, which is more like our table salt. Now in sodium chloride, each sodium atom is surrounded by 6 chlorine atoms. So if you take this sodium atom, you can see that you have 1, 2, 3, 4, and 5, one atom here, and 6, an atom behind. So you have a total of 6 chlorine atoms per each sodium atom, and vice versa. So if you now take a chlorine atom, like if you take this guy here, you can see that you're going to have 1, 2, 3, 4, and also 1 in front and 1 behind. As you all know, the electronic structure of sodium is such that you have 1 electron in the outer shell, 1 valency electron, and chlorine has 7 electrons in its outer shell. So for both of these atoms to obtain the octal stable state, one has to give up its electron, which is the sodium atom, and one has to receive an extra electron, the chlorine atom. So the sodium atom gives one electron to the chlorine atom, and because the sodium atom loses one electron, it becomes positively charged. And because the chlorine atom accepts an extra negative charge, which is the electron, it becomes negatively charged. Now, you all know that positive and negative attract each other, but positive and positive repel, or negative and negative repel. Now the sodium is positively charged, the chlorine atoms, or the chlorine ions, so to speak, are negatively charged. So these two, they attract each other. So there is what we call an electrostatic force that each sodium atom exerts on its 6 surrounding chlorine ions. So this is what holds the ionic solid together. So this is just an example of sodium chloride. So if you have any other ionic compounds where you have this donation and acceptance of electrons by atoms in the solid, the forces that hold the solid together are these electrostatic attractions between the ions inside the solid. Now the case of metallic solids is interesting, and you can see here we have a metal. So an example here would be sodium. So you know sodium from the previous example that it is one electron in the outer shell. So in a sodium metal, you'll have all of the sodium atoms giving off one electron. So you have sodium plus, and electrons surrounding them. So schematically it will look like that, where these positive circles are the sodium core ions, and they are surrounded by a sea of electrons, so to speak. So the forces now that hold the lattice together arise from an interaction between the positive core ions and the surrounding free electrons. Remember that the core ions are positively charged and the electrons are negatively charged. So this attractive force holds the metal together. And it's very important to see here that we don't have any holes. Okay? I'll get back to this later as we study electrons and holes in following slides. But it's just important for you to see at this point that the metal consists of positive core ions surrounded by a sea of electrons. The concept of a hole really doesn't apply here. Now for the case of a covalent solid, we have here the example of a diamond lattice semiconductor like silicon. As you saw in chapter 2, each atom shares its valence electrons with its 4 neighbors. So the bonding forces arise from a quantum mechanical attraction between the shared electrons and the positive nucleus of the atoms. So if you remember that silicon has 4 electrons in its outer shell, and so it needs 4 other electrons to obtain this octal state. So if you take one silicon atom here, you can see that it shares 2 electrons with each of its neighbors. So these lines here indicates a bond or an electron. So you have two electrons here being shared by this atom and that one. And remember that at the center, or at the nucleus of these atoms, the nuclei of these atoms is positive, and you have a negative electrons. So you can imagine that you have a positive and negative, and then you have positive there. So this is what holds the covalent solid in place. Now the two electrons, these electrons here, belong to the bond and are indistinguishable, except that they must have opposite spins to satisfy the Pauli exclusion principle. So this Pauli exclusion principle is very, very important in the formation of bands, as you'll see as we proceed. Now, as isolated atoms are brought together, the forces of attraction and repulsion between the atoms will find a balance at the proper interatomic spacing for the crystal. In this process, important changes occur in the electron energy levels, and these changes result in varied electrical properties of solids. So each if you take one element, it's different from the other, and some elements have more electrons in the outer shell, some have less electrons. So you can imagine that there's going to be a variation in the interaction of the electrons as you bring atoms of different kind of elements together. That's why we see that many solids behave differently, because they have different electronic structures. That's why some metals are some solids like metals are conductive, some solids like insulators are very resistive, and some solids like semiconductors, you have intermediate conductivities. So this all has to do with this the electronic structure of the solid. Now, before we get deeper into the formation of bands, it's very important to recall how we fill up energy states in an isolated atom. When we do that, we usually consider three things. So we have what is called the Pauli exclusion principle. What this principle states is that no two electrons in an atom must have the same quantum number. So they can have everything else can be the same, but they should have at least, different spins. So the spin is also part of the quantum numbers. And you have the off-band principle, which states that orbitals of the lowest energy are filled first. So if you are filling energy levels, you have to start from the bottom going up. And the Hans rule states that multiple orbitals of the same energy must be filled in such a way that you put one in each before you double up. So if, for example, at this energy level, if we have two states, for example, like that, and you can have two electrons in each state, so you have to go up and up. So once you fill these two states, you then double up. So if you have two states like that, you can't do that and having this state empty. So you have to fill one each before you double up. And here's an example. So we have our silicon, which contains 14 electrons. So if we are going to fill this, I'll just redraw this here so that you see how we fill it up. We have that, and we have that. So you can see you start by putting one here, then you put the second one there, then you come up here, you put one and you put the second here. but here you have multiple states of the same level, so you put 1, put 1, put 1, and then after that you double up. Okay, and then here you also do the same, like that, and then we are left with 2 electrons, so you put 1 here, you put 1 there. You can't put 1 here because you have to put 1 in each before you double up. So you know that this is energy level 3, so this is our N equals to 3. This is our outer shell, and in the outer shell you have 1, 2, 3, 4 electrons, and this is energy N equals to 2, you have 8, and N equals to 1, you have 2. Here we have the representation of the silicon atom. So you can see you have your nucleus, contains 14 protons that are positively charged, and around it you have all these electrons. And in terms of energy level, you can represent it like that. And the Coulomb potential now that is exerted by the nucleus on the electrons is given by this formula here, and you can see that r is the distance from the center of the nucleus. The Coulomb potential actually decreases with increasing distance from the proton, so you can see it's eventually proportional to Q here, to R, I mean. As you will see later, in a silicon crystal, when we bring individual atoms very close together, the S and P orbitals overlap. So you remember we have S, so in the N equals to 3, we have S and P, so we have 2 electrons in the S, and then we have 2 electrons in the P. So this is the pre 3P and 3S. So now these are the energy levels in a single atom, but when you now bring these atoms together, the S and P orbitals, they actually overlap. So you have your S orbitals, which are spherical, and you have here your P orbitals. So that's why we have here 3 of them. So you have 1 in the Y, 1 in the X, and 1 in the Z, for example. So you have this 1, 2, 3, like that. And then the S, this guy here, is spherical. Now when you bring silicon atoms together, so when the S and the P overlap, they form what we call a hybrid structure, which is sp3. So S for the S and P for the P. So these are sp3 hybrid orbitals. So you have 1 in the Y, and you also have another one in the X, and you also have 1 in the Z. So you have these hybridized orbitals, which are very, very, very directive. So the negative part of the P orbital cancels the S type wave function, while the positive part enhances it, thereby leading to a directed. So they are very, very directive bonds in space. That's why we end up having this tetrahedral arrangement where each bond is something like 109 degrees, like that. Now, another new thing to understand here is that these linear combinations of atomic orbitals, so when you bring these atoms together, you form linear combinations, and we call them the LCAO or hybridized sp3 orbitals point symmetrically in space along the four tetragonal directions to form this tetrahedral structure. So you can see here now you have the tetrahedral structure where you have one atom being bonded to four other atoms, and the bonds are equally spaced in space. And when you do a 2D representation, you can just do it like that, for example, and you can put two bonds like that, where the two bonds represent the two electrons that are being shared by two atoms. Now this part now shows you the formation of what we call bonding and anti-bonding orbitals. Now here it's important for you to remember that the electron actually orbits the nucleus in a wave formation, so it's more like a standing wave, and this wave function is usually represented by psi. So that's the wave function of the electron as it orbits the nucleus. So in this diagram here, you have two atoms which are separate from each other. So the dot here represents the nucleus of the first atom, and the dot here represents the nucleus of the second atom. And here you have the electron wave function. So when the atoms are split together like this, you can see that between them, right between here, you can see that the wave function is very, very low. Now if you bring them together now, bring them closer to each other, you'll find that these wave functions, they will interact or interfere with each other, and when they are in phase, they will constructively interfere. So here we can say they will constructively interfere, and when they constructively interfere, you remember when we did the double slit experiment, when you have a trough and a trough, you get a double trough. When you have a crest and a crest, you get a double crest, like that. But if you have a trough and a crest, you get nothing. So when they destructively interfere, you get nothing, right? Such that if you get the probability density function, which is something like the square of this function there, of the wave functions, if you get the square of that, you get the probability density function. You will see that if you look between the atoms, when they constructively interfere, the probability density function is very low between the atoms, which means that you don't have an electron there. But when they constructively interfere, you'll find that the probability density function is much higher, which signifies a covalent bond. Okay, and because here you have electrons and there is an interaction between the two nuclei, so one nuclei from this atom here and another nuclei from that atom. Both of these nuclei are positively charged, and they are interacting, or they are attracting these electrons. So because of this, the energy level of these electrons is lowered. See, the energy level is actually lowered compared to the anti-bonding state, as you can see there. So that's why the anti-bonding state has a much lower energy, because the electrons are being attracted by two nuclei, like that. And the gap between this anti-bonding and the bonding one is what we call the energy gap. And the energy gap is simply now the energy that you need to give to these electrons to make them free. Okay. Now the previous slide gave us a case of two atoms, and we did a thought experiment where we brought these atoms close together, and their wave functions destructively interfere to form the anti-bonding, and they constructively interfere to form the bonding state, where if you take the square of these wave functions, you get the probability density functions. And we found that in the bonding state, you have a very large probability density function between the two atoms, which represents a covalent bond. But for the anti-bonding, because they are out of phase, so to speak, you have a destructive interference. So at this middle of the atoms, you get a very, like, the probability density function is 0, so that says you don't have any electrons there. Now in this example, now we expand our thought experiment to n number of atoms, and the atoms in this case are silicon. You can see here you have your n equals to 1 here, and then you have your n equals to 2 over there, and then you have your n equals to your n equals to 2 ends here, and then you have your n equals to 3 starting from there. So this is like the 1s, this is the 2s, this is the 2p, and then this is the 3s, and then this is the 3p. So remember that in silicon, in the outer shell, so in the third outer shell, you have 2p, so these are 3p, and then you have 3s. So if you check the 3p, you have 6 states, so you can have 1, 2, 3, 4, 5, 6 electrons, so you have 6 states. And if you take n number of atoms, you have 6 n states, and you have 1, 2, 3s states. If you take an n number of electrons, you have 2 n states. And in the 3s orbital, you have exactly 2 n electrons, because they are all filled. But in the 3p orbital, you have 6 n states, but only 2 n states are filled. So you have 2 n electrons and 6 n states. So now you can imagine, now you bringing now these n number of atoms together, and as you go to your left here, you are bringing the atoms closer and closer together. Now you see that as you bring them together, just like in the case of the two atoms, the wave functions of the atoms will interact, and if they are in phase, they will constructively interfere, forming the bonding state. And if they are out of phase, they will destructively interfere, forming the anti-bonding state. But because of the Pauli exclusion principle, remember, you cannot have electrons occupying the same energy level. You can have at most 2 electrons at the same energy level. So if you have an n number of electrons, you will have to split this into about n states. So you have about 4 n states. Remember that if these p and s orbitals, they overlap to form the 3sp3 orbitals, the hybridized. So you have 4 of these guys here, and so you have here 4 n states if you consider n number of atoms, but you have 0 electrons because the probability density function here is going to be 0 because they will destructively interfere. So you end up having this band, and then you have that band. Now, as you move this closer and closer and closer together, the inner energy levels, like the F, the 2p, they will also start to interfere, and they will start also to split. And the gap between the bonding, the anti-bonding and the bonding states is what we call the band gap. Okay. And at 0 kelvins, every state in the valence band, so the bonding state, we call this the valency band, because this is where we have the covalent bond, so to speak. So we call that the valence band, and at 0 kelvins this will be filled, while the conduction band, which means this band here, the anti-bonding, will be completely empty. Now we call this one the conduction band because once an electron goes up here, it means that it is free from the influence of the atoms in the lattice. So it's free to move around and carry electricity. Now this arrangement of the completely filled and empty energy bands has an important effect on the electroconductivity of solids, as we'll see later on. Okay, now for some of you, this could be like too much data, like too much information to process. So here I've prepared a simple representation of what we've been talking about. So for this simple representation, I've chosen bands of crystalline silicon. Now, crystalline silicon has a tetrahedral lattice structure, which is a direct result of the electronic structure of the silicon, which is 4 valence electrons. So when the silicon is unbonded, when you consider just one silicon atom, you find that you have 2 states and 2 electrons in the 3s energy level, and you also have 2 more electrons in the 3p. Now, such a configuration only allows 2 covalent bonds to be performed with neighboring silicon atoms. So in order now to maximize the number of bonds possible, the S and P electronic states combine to form 4 sp3 states. So these P and S orbitals actually overlap and form these hybridized sp3 orbitals. Now the sp3 orbitals permits a bonding with up to 4 silicon atoms at the tetrahedral angle. So because of this, you are now able to have the tetrahedral arrangement where each bond is around 109 degrees from the other. So interaction between the 2 atoms, electrons lower the energy state. Therefore the sp3 energy splits into bonding and the anti-bonding level. So you remember, when you now put or bring silicon atoms together, the wave functions of the electrons can either constructively interfere to form the bonding state, or they can destructively interfere to form the anti-bonding state. Now, this is very, very important. In a real solid, there's Coulomb interaction. There's Coulomb interaction between the atom cores and the electrons, and so the bonding and antibonding energy levels split, forming a continuum of extended states. And the reason for these extended states is mainly the Pauli exclusion principle, which states that you cannot have two electrons having the same quantum numbers. You cannot have them at the same, you can have at most two electrons at the same energy level with opposite spins, as you well know. Now, if you consider a solid, you have millions and millions of electrons coming together, so they cannot fit in only two states, so you get this continuum of extended states. So these are what we call the extended states. The extended states. Or simply you can call them bands. You can use the word band there. So the antibonding band, we call that the conduction band. And the bonding band, we call that the valence band. So this is called the valence band because these electrons are covalently bonded. They are forming the covalent bonds between the atoms. But this one is the conduction band because once an electron finds its way in the conduction band, it is free to move. It's no longer bound by the attractive force of the atom's nuclei. It's actually free to move around and conduct electricity. So we'll look at that later and let's try to understand what that really means. Now we can use this simple representation now to distinguish metals from semiconductors and semiconductors from insulators. So here we have three illustrations. So one is for an insulator, one is for a semiconductor, and one is for a metal. And we assume that the temperature here is 0 kelvins. So we are at 0 kelvins. Now, if we start with the insulator, you can see that at 0 kelvins, the valence band of the insulator is filled with electrons. It means you don't have any empty spaces. So by empty space, we usually call this empty space a hole. Okay. So we are saying that you have only electrons here. All states are filled. You don't have any empty states or any holes. The same applies to the conduction band. So in the conduction band, it is also empty. Okay. But it's very important for you to understand here that although the conduction band is empty, there are no holes in the conduction band. Holes only exist in the valence band when the valence band has no electron. So if an electron comes from here and goes there, it leaves behind a hole. All right. But when an electron falls from the conduction band and back to the valence band, it does not leave a hole. So what exactly is a hole? So now if I draw, for example, silicon like that, so this goes on and on in all directions. So these two electrons, they represent the bond. That's the covalent bond between two silicon atoms. Remember that silicon has 4 electrons in the outer shell, so it needs 4 more. So if it shares 1 electron with 4 other silicon atoms each, then it can obtain this octal state. So the covalent bond here represents 2 electrons that are being shared by these 2 atoms, this guy here and that one over there. So this is what is here. This is the covalent band where you have the bonds. Now, if an electron now is excited from the valence band to the conduction band, it means that you have broken a hole here. Okay? So if you break a bond here, you leave behind a hole. Okay? You leave behind a hole. So that's the concept of a hole. So a hole is more like a broken bond, so to speak. Right? Now, what is the conduction band? So remember that this is just an energy scale. So this is just reference to an energy level of the electron. Okay, so when you break the bond, the electron becomes free. It's just free in the lattice. Okay, it's not at a state, it's just free to roam around like this. So this free electron, we say, it's in the conduction band. Remember, this is just energy, energy level. This is just an energy level. So this guy here is said to be in the conduction band, but there are no bonds here. So if this electron goes back here, it does not leave behind a hole. Okay, so in the conduction band we can only have electrons. Okay, it's just a level, an energy level. Now, it's important to see that at 0 kelvins, because you have the valence band filled and the conduction band empty, the insulator does not conduct. Okay, so for conduction to occur, electrons should have empty spaces where they can go to. Okay, so if an electron is here, then there should be nearby empty spaces where the electron can easily go to. So if the electron can do this, then it can actually conduct electricity. Excuse me. Now, for conduction to occur, electrons should have empty spaces available that are nearby. So that's very, very important. The empty spaces should be nearby. Now, if you look at the insulator, you can find that in the valence band, because the valence band is filled with electrons, there are no empty spaces where electrons can actually go to and have a net motion, so to speak. I'm using the word net here because electrons are always moving, but you find that if the valence band is filled, it means if one electron goes this way, there will be another one going the other way, such that there is no net motion. Okay, you'll see later as we proceed with the chapter that electrons are always in a motion that we call thermal random motion. If you increase the temperature a little bit, electrons start moving. Now the situation here is at 0 kelvins, so it means that the electrons are not moving, so there is no conduction. But if you increase the temperature, let's say you are now at 300 kelvins, the electrons will start moving around with this thermal random motion. So it's the motion of electrons due to temperature. And because the motion is random, you don't have a net motion, so you cannot have conduction of electricity. Okay, and the empty spaces where electrons can go to are in the conduction band. But these states are not nearby. They're very far from the conduction band because insulators have a very large energy gap. So this energy gap is usually greater than 5 electron volts. So even if you increase temperature to 300 kelvins, you have an insignificant number of electrons that can actually gain enough energy to reach the empty states in the conduction band. So an insulator is insulating even when you go to high temperatures like room temperature. Now the difference now between an insulator and a semiconductor is that the gap of a semiconductor is small. For example, the gap of silicon is around 1.1 electron volts. So this gap is small enough for electrons to actually be able to overcome it. So for silicon, for example, at room temperature, you have around 10 to the 10 electrons in the conduction band. So just this energy from heating, like at room temperature, you can actually excite electrons to the conduction band. And when you excite electrons, you are more like breaking bonds. You are breaking these bonds, so you leave behind holes. So when we say 10 to the 10, we usually say 10 to the 10 electron hole pairs, because for one electron, you leave behind a hole. So electrons and holes, they occur in pairs. So you have these electron hole pairs. Okay. So this is basically the difference now between an insulator and a semiconductor. At 0 kelvins, they are the same. No conduction. They behave exactly the same. But when you increase the temperature a little bit, okay, so at 0 kelvins, insulators and semiconductors are basically the same. But the only difference now is when the temperature is a little bit higher than 0 kelvins. For example, when you're at 200 kelvins or when you're at 300 kelvins, that's your room temperature. You'll find that at that temperature, the semiconductor will have a considerable number of electrons in the conduction band and some holes in the valence band, whereas an insulator will remain like this, filled and empty. The reason for this is because the band gap of the insulator is very large. So you remember we said it's something greater than 5 electron volts, whereas that of a semiconductor is usually less than 3 electron volts. So this energy gap, which is equivalent to the energy that is required to break the bonds. You remember we said you've got something like silicon bonds like that, where these two lines represent 2 electrons. So for the electron to be excited to the conduction band, that's equivalent of breaking this bond and have the electron free to conduct electricity. So this Eg is essentially the energy that is required to break this bond. So if the band gap is small, it means you need a small amount of energy to break the bond. But for insulated, you need a very large amount of energy. So because of this, now we can actually control the conductivity of a semiconductor. You know, if you apply some external excitation like heat or light or even mechanical pressure, you can actually generate electrons. So a semiconductor is something that can be made to conduct or to insulate, depending on the application. The fact that we can control its conductivity, we can actually use it in making electrical devices. We'll look at this later as we move through the chapter. Now, the metal now is different now in that you always have electrons in the conduction band. So you can see here at 0 kelvins you've got the metal having a partially filled conduction band, which means it's always ready to conduct electricity. Another model of a metal is when the covalent band actually overlaps with the conduction band, as you can see here. And in both models, you can see that you have electrons that are very close to empty states that are nearby. So these electrons can go to these higher energy states, these empty states, and actually conduct electricity. So even if you have a partially filled conduction band, it means you have electrons here and empty states that are available for the electrons to go to. So you'll find that metals readily conduct, whereas semiconductors can be made to conduct or not conduct. Like their conductivity can be varied over a wide temperature range or any other form of external excitation, whereas the insulator is always insulating in most cases. So that's basically the difference between these three. Now, another important distinction to make now among semiconductors is whether they are direct or indirect. Now, you remember we said that the electron orbits the nucleus in a wave function. Now, the wave function of an electron is given by this equation here. So we call it psi. And psi is given by U, kx, comma x, e, j, kx. Now in this equation here, k is the propagation constant wave vector. And kx simply means that we are moving in the x direction. So we can have this is psi y or psi z, depending on the direction that we are moving. So remember, a lattice is a periodic. You have this repeating pattern. The unit constant, the lattice, the unit of the lattice repeats itself over and over again. So that's what gives you this kind of a propagation constant wave vector. So now we can actually now plot energy as a function of wave vector, or the energy of an electron in this K space, so to speak. Now, what's important to note here is that this K vector, or this propagation constant wave vector K, can actually be shown to be equal to the momentum through this relationship here. So your psi, your P is actually proportional to your momentum. Okay, so what it means is that if you have this EK diagram, this EK diagram is actually equivalent to an E momentum diagram. Okay, so you can think of this as the energy of an electron as a function of momentum, because the momentum is simply equal to Planck constant times the K wave vector. So this would be that over this Planck constant with a bar, which is h over 2 pi. So if you see any EK diagram, for it to be easy for you to understand, you can think of it as an energy versus a momentum diagram. So why is this important? Now, this is important in understanding direct and indirect semiconductors, in that when the valence band maximum is at the same K value as the conduction band minimum, when the maximum and the minimum are aligned in K space, we call that semiconductor a direct semiconductor. So what this means is that when an electron now falls from the conduction band to the valence band, it does that without a change in momentum. Whereas an indirect semiconductor has the valence band maximum at a different K value as the conduction band minimum. So when an electron now falls from the conduction band to the valence band, it has to do so through a change in momentum. So this is direct in the fact that the electron falls to the valence band without a change in momentum, and in most cases, all the energy that the electron loses when it goes to the valence band is given off as light. Okay, but most of the energy that the electron loses as it falls down to the valence band in an indirect semiconductor is mostly given off as heat, because it has to go to do so via trap states. Okay, so that's the main difference between a direct and indirect semiconductors. So you'll find that when we make photoconductive devices that can emit light, so to speak, we usually use direct semiconductors. And things like silicon. So you remember silicon is an indirect, looks like that. So silicon cannot be used in photoconductive devices. Okay. So here are some of the examples of direct semiconductors and indirect semiconductors. So we are saying in an indirect semiconductor, an electron makes the smallest energy transition from the conduction band to the valence band without a change in the K value, and this is equivalent to no change in momentum. Examples of direct semiconductors are gallium arsenide, indium phosphorus, zinc sulfide, zinc selenide, and cadmium sulfide. In indirect semiconductors, a transition from the minimum point in the conduction band to the maximum point of the valence band is only possible with a change in K. So the electron has to change its momentum as it transitions from the conduction band to the valence band. And popular examples are silicon, germanium, silicon carbide, aluminum arsenide, and gallium phosphorus. Now, a compound semiconductor, for example, you remember the zinc blende semiconductors, for example, aluminum, gallium arsenide, where we have X here and then here 1 minus X. It's arsenide. So these compound semiconductors can actually have many conduction band minimums depending on the crystal direction, so to speak. So for example, here we have aluminum gallium arsenide where X is equal to 0, giving us simply gallium arsenide. Gallium arsenide has 3 conduction band minimums you have this capital letter L, you have this capital gamma, you have this chi. All these are conduction band minimums in different crystal directions. Now, the way that you can decide whether this is a direct or indirect semiconductor is by looking at the lowest conduction band minimum, which in this case is gamma here. Now, because the lowest of these minimums is at the same K value as the conduction band maximum, this semiconductor becomes an indirect semiconductor. Okay, and one way to understand that is because we always assume that electrons, they always take the lowest available energy level, so electrons will all sit at the lowest minimum of the conduction band. So in that case, the transition from the conduction band to the valence band is going to be from the lowest of the conduction band minimums to the top of the valence band. So this becomes an indirect semiconductor. Now you can see that as you add aluminium into this gallium arsenide semiconductor to make it aluminium gallium arsenide, the conduction band minimum, the position of these conduction band minimums actually vary, such that when you increase aluminium and decrease gallium to a point where you have aluminium arsenide, where X becomes 1, in that case your X would be equal to 1, and then you end up with aluminum arsenide, you find that the gamma here, the conduction band minimum gamma, actually moves up further away from the valence band maximum, such that by the time you get to aluminum arsenide, it is the minimum chi that is the lowest. So in this case, you see that this semiconductor becomes now indirect. Okay, so what we can learn from this example is that we can actually tune our semiconductor to make it direct or indirect. We can even tune our semiconductor to control the size of our energy gap. Now, the importance of that is that you can actually change the color of the light that the semiconductor emits when electrons fall from the conduction band to the valence band. Remember that with your semiconductor, your EC and your EV, as the electron falls from the conduction band to the valence band, the light that is given off is equal to the energy gap, Eg. So if you can vary now the energy gap, if you can vary the energy gap, you can actually vary or control the color of light that you want to be emitted when electrons fall from the conduction band to the valence band. You can see from this graph here the effect of now changing the aluminium fraction. So when the aluminium fraction is 0, where you have gallium arsenide, you'll see this extreme case here, which is the one that's shown in A here. And when and if you keep adding more aluminium and decreasing gallium, you can see that your gamma moves up further away from the valence band up until you reach this point here, which is around 0.38. So going all this way your semiconductor is a direct semiconductor. Why? Because it is the conduction band minimum that is at the same K value as the valence band maximum that is the lowest among all the minima that you have. So it's direct. But if you add more aluminium and decrease gallium and decrease the gallium fraction, so to speak, you find that the chi now becomes the lowest of the minimas. So in that case, the semiconductor becomes indirect in that case. So from here going there, you get an indirect semiconductor. So if you want the aluminium gallium arsenide to be used for photoconductive devices, you should make sure that your aluminium fraction is equal or less than 0.38, because that is when the semiconductor is a direct gap semiconductors, where all the recombination processes result in a radiation or you get radiative recombination. You get light being emitted as the electrons fall from the conduction band minimum to the valence band maximum. So that way you can actually tune now your light, the amount of light or the color of light that you want. You can actually tune by controlling the fraction of your aluminium, as you can see from this graph here. Okay, so now let's understand more deeply what we mean by electrons and holes. So these are the charge carriers in semiconductors. We have electrons and holes. So you remember that we said at 0 kelvins, you've got a filled valence band and an empty conduction band. So this is EC, this is EV. But as the temperature of the semiconductor is raised, some electrons are excited to the conduction band, leaving behind holes. So we call this thermal excitation. Thermal excitation. And these electron and hole, they occur in pairs, so we call them electron and hole pairs, because for every electron you leave behind a hole. Now, if the conduction band electron and the hole are created by excitation of a valency band electron to the conduction band, they are called an electron-hole pair, abbreviated EHP. The equilibrium number of electron-hole pairs in pure silicon at room temperature is about 10 to the 10 electron-hole pairs per cubic centimeter, compared to the silicon atom density, which is about 10 to the 22 atoms per cubic centimeter. So you can see that at room temperature, so this is you'll have 10 to the 10 versus 10 to the 22. So you can see that you have 12 orders of magnitude difference. So the conductivity of pure silicon at room temperature is very, very low, because the electron hole pairs are much smaller. The number of these electron hole pairs is much smaller compared to the density of silicon. So the conductivity is not going to be very good. So because of this, we must find a way to increase these carriers, these charge carriers in this semiconductor. We must find a way. And the way we do that is by doping. Okay, so this illustration here simply help us to understand that when you have the case at 0 kelvins where the valence band is filled and the conduction band is empty, you can never have any conduction. The reason for this is because electrons, so to begin with, electrons are always in this thermal random motion, so they are always moving. But when the valence band is filled, these random movements of electrons always cancel each other. So for an electron moving in this direction, you also have another electron moving in an exactly equally and opposite direction, such that you have no net motion of electrons. But now if you create an electron hole pair where you have an electron here and a hole there, then the net current now is going to be equal to plus Q Vj. So the more you have, the more current. So if you have an n number of these, then you have plus Q and Vj. So we need now to increase the number of these electron hole pairs for us to have more conductivity in our semiconductor. Okay, so now let's see how we can simplify now our Venn diagrams from that to just showing the conduction band minimum and the valence band maximum, like that. Now to do this, we have to understand that an EK diagram like the one we discussed in the previous slide is a diagram which plots the total electron energy. So by total we mean potential plus kinetic as a function of the crystal direction, electron wave vector, that's our K, and this K is proportional to the momentum, and therefore the velocity at some point in space. So if we have an electron here, what it means is that this electron, the total energy of the electron is equal to potential energy plus kinetic energy. And the bottom of the conduction band corresponds to 0 electron velocity or kinetic energy, and simply gives the potential energy. So from here to there you have your potential energy, and from the bottom of the conduction band going up you have your kinetic energy. So once an electron rests at the bottom of the conduction band, it has 0 kinetic energy, and its energy is equal to the potential energy. The same applies for holes. The top of the valence band corresponds to 0 kinetic energy. So if a hole is here, the hole is here, it means it has 0 kinetic energy. Remember that hole energy, this plot is in electron energy, but for holes the energy increases downwards. So here the top of the valence band corresponds to 0 kinetic energy for the hole. Now, for simplified band diagrams, we plot the edges of the conduction band and valence band. In other words, we only plot the potential energy as a function of position in the device. So now, instead of having instead of plotting what we have, our EK diagrams like that, for simplification, when we deal with devices, we only plot the bottom and the top of the valence band and conduction band as a function of position. So this is X, position in the device. Now, energies higher in the band correspond to additional kinetic energy of the electron. So if I have an electron here, it means it has potential energy up to here, and this difference is the kinetic energy. Also, what's important to realize is that the fact that the band edge corresponds to electron potential energy, which means that the variation of the band edge in space is related to the electric field at different points in the semiconductor. Remember that we are plotting here the energies as a function of position. So if I have a slope, it means that I have different potential energies at different positions, and that corresponds to an electric field. Remember that an electric field is a potential difference. So once I have this difference, it means I have an electric field. So you will find that electric fields are represented by slopes in the bands. Now let's see what happens by looking at this example here. So if an electron at a location A, this location here, sees an electric field given by the slope of the band, which is the potential energy, and gains kinetic energy at the expense of potential energy by moving to point B. So it gains kinetic energy at the expense of potential energy by moving to point B here. The electron then loses the kinetic energy to heat by scattering mechanism and returns to the bottom of the bands at B. So the electron comes here, and then it loses and it goes all the way to B. And it does that by scattering mechanisms until it reaches point B, like that. So now what's important to take from here is that we are going to represent an electric field by slope of the band edges. So if you see something like that, you should know straight away that you've got an electric field, a difference in potential, which is an electric field, and then the slope increases in the direction of the electric field. So in this case, the electric field will be going from left to right, and electrons, they always move in the opposite direction. So electrons will move in the opposite direction, downhill, so to speak. So the electric field increases uphill, while the electrons motion is downhill. Another very important concept is that of the effective mass of an electron. Now, the true mass of an electron doesn't change whether the electron is traveling in free space or in a vacuum or in a solid like the silicon semiconductor. The true mass of the electron is the same. The effective mass, however, changes, because the effective mass now takes into account the obstacles that the electron faces as it travels through the solid. So this is the periodicity now of the lattice, if you think of a crystalline semiconductor. as you can imagine, when an electron is moving in a solid like the silicon semiconductor, it's going to be scattered by the atoms in the lattice, or impurities or defects. Its path is not going to be a smooth one. So when we use the equations of electrodynamics, like the usual equation that we use to model a certain concepts in physics, we should now substitute the mass of the electron with the effective mass when we now are considering semiconductors. Now, to calculate the effective mass, we should consider the shape of the energy bands in one-dimensional K-space. And to do that, we start with P equals to mv, where P is the momentum, m is the mass, and v is the velocity. Now, if you take E equals to half mv squared, and here you substitute v for, in this case, from this guy here, you find that your v is equal to p over m. So if you take this guy here and put it there, you get half mp squared over m squared. Now these m's cancel, and you are left with half p squared over m. Now, if you recall, when we looked at the wave function, the EK diagrams, we saw that your momentum is actually equal to h bar k, where k is the wave vector. So the k space, the k propagation wave vector, is actually proportional to the momentum, and the constant of proportionality is the h bar, which is Planck constant divided by 2 pi. Now, from here, if you substitute now your P for h bar k, you now get E is equal to half h bar squared divided by m by k squared. So your energy now you express is in terms of the k vector. And then now if you, so from just by looking at this, you can see that your energy is parabolic with the k wave vector. That's why we have, if we draw our EK diagrams, we always have something like that, because our energy is actually parabolic with respect to the k wave propagation wave vector. Now, from here, if you take the second derivative of E, you find that the second derivative of E is equal to h bar squared over mn star. So the reason why we take the second derivative is because we want to get rid of this k here. And if you do that, you find that your m is equal to, from here, you see that your m is equal to h bar squared over t squared E over dk squared. Now you see that if you take the first derivative, you kind of get the slope of a line, the slope. But when you take the second derivative, it actually gives you what we call the curvature. So this second derivative here is actually the curvature. So you find that your effective mass is actually proportional to the, is inversely proportional to the curvature. So if we found that the effective mass is equal to h bar squared divided by the curvature of the conduction band. So if we have, for example, two semiconductors, one which looks like that and the other which looks like this, it means that here the curvature here is small, but here the curvature is big. So it means that this semiconductor here is going to have, because it has a small curvature, it's going to have a large effective mass, whereas this guy here is going to have a small effective mass. Okay, so the effective mass is really a function of the band curvature, and so it means that the electrons in this semiconductor, for example, are heavier than those in this semiconductor. So from here you can guess, for example, that the mobility, or the way the motion, the speed at which electrons move in this semiconductor must be faster, because lighter things move faster than heavy things, right? So if the effective mass here is large, it means the speed at which the electrons are going to move, or the electrons are going to respond to an applied electric field, is going to be slower, because they are heavy, so to speak. Okay, heavy by taking into account the obstacles that the electrons face as they move in the solid. Remember, the true mass of the electron is always the same. Okay, so if you remember, we had gallium arsenide with 3 conduction band minimums. So it means that if the minimum is in this gamma here, which was the one that had a large curvature, so it means here the mass is going to be smaller compared to the other large conduction band minimums, like the chi, so to speak. And another important thing is that this concept of the effective mass actually is in favor with the concept of a hole. So you find that here you have a positive curvature, but in the valence band you have a negative curvature. So what this means is that electrons that are in the valence band have a negative mass, and they are negative. I mean, the electron is negatively charged. So you'll find that a particle with a negative mass and negatively charged will move in the same direction as a particle with positive mass and a positive charge. So we can actually account for the movement of electrons in the valence band with a hole. Okay. So a more realistic band structure is presented here. So in this case, we have examples of silicon and gallium arsenide. So you can see that depending on the crystal direction, so here is the 111 direction and here is the 100 direction, you will find now different minimums depending on the crystal directions. For gallium arsenide, it seems that the lowest it is, you have many minimums, but the lowest minimum is at the same K value as the maximum of the valence band. So this is now a direct gap a semiconductor, whereas silicon has a conduction band minimum. The lowest of the conduction band minima is at a different K value as the maximum of the valence band. So this becomes an indirect semiconductor. Now when we try now to calculate now the effective mass, we then kind of like take the geometrical mean of some of these band curvatures. So we take a geometric mean when we calculate the effective mass. So this is the density of states. If we calculate, for example, the density of states effective mass, so density of states effective mass, we are going to get some kind of a geometric mean. So we need the density of states effective mass when we try to count the number of electrons in a semiconductor. So we use the density of states effective mass. But when we try to calculate things like the mobility or the electric field, we usually get the the conductivity effective mass, which is more like a harmonic mean of these band curvatures.